basic algebra. So we'll have an allele, and since dominance and recessive is irrelevant here, we simply refer to it as A1 and A2. And each one has a frequency. And for traditionally, this is referred to as the frequency of P and Q, because we're just dealing with the type of algebra right now. So if there are only two alleles, what must P plus Q equal?
1.
P plus Q must add up to 1. So can we demonstrate, if we just make these assumptions, that there will be no change in allele frequencies? All right, your textbook shows in detail, and I'm just going to show you this without the detail, is that you can show that the distribution of genotypes in the next generation, if you assume, we're assuming something whose genetics works like us, a diploid species, then you're going to have the distribution of genotypes in the next generation will be P plus Q, that quantity squared. And you ought to know from your algebra that comes out to P squared plus 2PQ plus Q squared equals 1. Have you seen that type of equation before? It's basically your old quadratic equation. So this is the distribution in the next generation of genotypes. What must P squared be the distribution of which genotype? The frequency of what type of genotype? Q squared must be what? Yeah, it has to be of A2A2. And this 2PQ must be the heterozygotes. So this gives us the genotypes of the heterozygotes in the next generation. But what we want to know is, has the allele frequencies changed? And so we have to do a little bit of algebra and substitution. So after one generation, we want, what would be the frequency of A1? Well, we see that there are P squared, so it's going to be partly the A1, so we're going to have P squared, because all of A1 is the allele A1. And here we have 2PQ, so half of 2PQ must be the partially a frequency of A1. So basically, we have P squared plus 1/2 of 2PQ. Must be the frequency of P in the next generation, because half of them come from here, and then some of them come from here, and then we're getting half of these. So what do we do with that? Well, if you do a little algebra, this comes out to P squared plus PQ. Now we do a little substitution. Because we know this here, we can make a substitution, and Q, remember, must equal to 1 minus P. So now we have P squared plus PQ equals P squared plus P 1 minus P equals P squared plus P minus P squared equals P. Which means that after one generation, there has been no change in the allele frequency of P. And the same thing applies if we did it with Q. And this also met the criterion that if we knew the allele frequencies, we could predict the genotype frequencies. Now, as I said, I went through that quickly, and I would expect that either in your notes or even better yet in your textbook, you might have to work through that a little bit, convince yourself that this actually makes sense. But this is, in fact, a demonstration that the frequency of A sub 1 has not changed from one generation to the next when we meet the requirements of the Hardy-Weinberg equilibrium. And you are predicting since the frequencies haven't changed, in the next generation, you're going to end up with the same genotype frequencies. It's predictable. Is it possible to make a numerical example? It is. And you can, if I do this on a test, and I will have this on a test. That's a hint, of course. You can certainly do this with any values and demonstrate arithmetically, if you follow that through, that you get the same value. Now, it's sensible to choose easy numbers. You could choose, 0.56832, or you could just say, 0.6 and 0.4, which is a little bit easier. And sadly, even when it's very simple arithmetic, I still have students who will want to ask if they can use a calculator to figure out what 4 times 0.4 is. I guess nobody really learns how to do mathematics anymore, arithmetic, but it should be, if you follow that equation, it's quite easy to work through a numerical example. Because of our laws today, I'm not going to do a numerical example because there's one in your textbook anyways. So that is the mathematics of Hardy-Weinberg. So what does it again do? It tells us that we've met assumptions 1 through 4, and allele frequencies haven't changed. If we also assume panmixia, it's predicting genotype frequencies, but even if mating is not random, the allele frequency still won't change. The problem there is that it will no longer be predicting the genotype frequencies. But evolution cannot occur if all 4 of those criteria are met. Now, are all 4 of those criteria met in populations? Well, obviously no, because evolution occurs. However, can we envision populations where some of those are mostly being met? Can we envision an allele, a particular gene locus that's not under any particular selection? Sure we can. There are lots of traits like that, like my old favorite, your little finger crooked or straight. That's probably not under any selection. Can we envision a situation where if there's no mutations? No, but can we envision mutation rate is so low that's not really making any much of a difference? Sure. Do we have isolated populations that don't have individuals entering or leaving? Sometimes we do. And although no population is infinite, it doesn't really have to be very large, on the order of 100 or more, before, in essence, it might as well be infinite in genetics terms. So we can certainly envision populations that are close to meeting some of these. Now, are there truly populations that show panmixia? Well, that's more debatable. People sometimes would use the Atlantic eel, which comes down from all the rivers of Europe and swims out in the middle, and then they have a great big mass of maters, all in this big mass of mating, but just because we don't see what their pattern is doesn't mean they're not making choices, so we don't really know if they're really random or not. Whether there's truly random mating is, I'm not sure about that, but at least you could envision it. So the value, however, of this is when we start relaxing the assumptions. If we say, okay, then what happens if we do have selection? And what happens if we do have a mutation? Or what happens if we start having individuals moving between populations? This is where, as I said earlier, your textbook now will start to have mathematical demonstrations of each of those. And they'll throw in what about a dominant trait versus a recessive trait, et cetera, et cetera. And I'm not going to hold you to any of that mathematics, just this basic Hardy-Weinberg. If you go to some university and take a graduate level course in population genetics, then you can have all of that mathematics to your heart's content. So what we're going to look at in non-mathematical formats is what happens when you start violating the assumptions of the Hardy-Weinberg equilibrium. And we've already, of course, looked at natural selection, but we will continue on that line by looking at some of the ways in which natural selection affects populations, a little bit more than we did before. And then we will briefly look at the mutation one, and then probably not today, but maybe the next time, look at the other two. All right, so natural selection. We already know what natural selection is, but we're going to start looking at a little bit more about how natural selection changes population, some of the different effects it can have. The first one to note is the strength of the selection. We often refer to the selection as the selection pressure. How much pressure is being put on the population by the environment? Stronger pressure means will lead to a more rapid evolutionary change. Of course, if pressure is too strong, you might end up with extinction. But assuming that evolution can occur and adaptation can occur, stronger selection makes more obvious modifications and more quickly. But even weak selection, very weak selection, can, given enough time, produce significant effects. Like if you want to take a look at this graph here. This is a graph. This is actually in terms of simulation. That's one of the things computers are good at. But what they've essentially done is we're looking at an allele B. It's one allele we're looking at how it might change in frequency. If its frequency changes, that's of course evolution. These are generations. That's a lot of generations, 1,000. It can happen fairly rapidly in bacteria, but 1,000 human generations takes you back pretty far. And what we're looking at is how the allele frequency of B changes, starting from a very low value, depending on the selection. So it can't start at 0. If it started at 0, it would never change. But it has a very low frequency. Let's say this is probably when it appeared in the population as a mutation. So it would start out as a low frequency. And what this is showing us is a strength of selection, basically from weak to strong. All of this is beneficial. It's always beneficial, but weakly beneficial to extremely beneficial. So when it reaches 1.0, when an allele reaches 1.0, we say that it is fixed. The frequency is 1.0, it's 100%, it's fixed. So how quickly does it reach fixation? Does it reach fixation more rapidly if it's strong or if it's weak?
Strong.
Yeah, the stronger the selection, the more rapidly it increases in frequency. But even the weak selection, although that has gotten nowhere near fixation, it's probably there about 5%, still an increase from an extremely low percentage to 5% is a significant modification. So all of these are changing the allele frequency, but the stronger the selection, the more rapidly the allele increases in the population, its frequency. We can also look at how it changes the traits. All of the examples, almost all the examples I've been giving you, probably maybe even all of them, have been what we call directional selection. Now I want to make it clear, notice these are all under natural selection. Directional selection, stabilizing, disruptive, are not something in addition to natural selection, they're just subsets of natural selection, different ways natural selection affects a population. The reason I say they've all been directional is if we look at what directional selection means. Then we'll look at a variety of examples. And here we have a trait, and it would have been nice if they put some axes here, but for this you might say this is the range of the trait, and this is showing its fitness, in other words, how good. Higher the value, the better it is for that environment, and this is the range of the trait. So let's say this is necks, how long a neck is. In the ancestors of giraffes, let's say this was the average value. There's a bell-shaped curve. Doesn't have to be bell-shaped, but we often show it that way. So here's the average length of a neck. Over time, what happened in the evolution of giraffes? The neck got what? Longer. So what happens to the mean size? It's moving in one direction. That's why it's called directional. It's getting longer. This is why our various examples we've cited have generally been directional. Antibiotic resistance is directional. The average value of the population is highly susceptible to the antibiotic. Then, as evolution evolves, it's moving in the direction of being less susceptible to the antibiotic. So what is really happening is the mean is shifting, and the reason is one end is being favored of the possible range of variation. The other end is being selected against. So this end is selected against, this end is selected for, and it pushes it in one direction, the average. Now, this does not have to be shaped, like I said, a bell shape, but it's a useful way to illustrate it. That's a directional selection, a natural selection. Here's an experimental, probably with some form of Drosophila. Looks like Drosophila anyways. And what they're basically doing is seeing if you can get fruit flies to be adapted to being drunk. Well, actually to live on alcohol. And what they essentially did in this study, if you look at that, is this particular gene, this allele I should say, this allele allows them to subsist on diets that include higher amounts of ethanol. Now, what they could detect this allele by running genotypes, gene sequences on fruit flies. And what we see is in control populations where the amount of alcohol remains low, or no alcohol, the ADHF allele does fluctuate because there are random effects going on there. But notice there's no real trend towards it increasing or decreasing. That's because it's not under any selection. So it may be affected by random events or something, but it's not being selected for or against. But then in populations of flies that are being reared in environments with a high alcohol content, what's happened over generations to the frequency of this allele? It's directed towards a higher and higher, basically, tolerance for alcohol and their ability to use alcohol. They probably go into delirium tremens if you remove their alcohol after a while. I don't know about that, but they're becoming highly adapted over generations to the alcohol in their diet, ethanol specifically. So that's a laboratory directional selection. A classic example of directional selection often cited is in the peppered moth, Biston betularia. The peppered moth is a wide distribution, but the story that we're looking at here is in Britain, British Isles. The peppered moth is interesting in terms of its color form. Each of these, you notice we have on the left one that is peppered and the other which is very dark. In the language that they use in genetics, and these are called morphs for different forms. What I want to be clear about is those are not different species. They aren't even different for whatever the word means, races. You can have in a set of eggs from the same parent moths both peppered and dark. This is just the kind of variation that occurs among the eggs. So some individuals in the same family might grow up peppered, the other is dark. It is a heritable trait. So this is all found in the same population. However, what happens to them later is affected by the environment. Moths, when are moths typically active, daytime or nighttime? So, yeah, they're active at night. So in the daytime, the main thing a moth wants to do is not get eaten. So it rests somewhere. What type of predator is strongly visual that might want to pick off and eat a nice moth? Birds. Birds fly around, they're very visual. They spot moth resting, makes a good meal. So here we have a tree trunk. This is a lichen. I like lichens because that's where tardigrades live, but lichens are also found on trees. You see them on the branches here when they fall down. But here's a large piece of lichen. There's a dark morph. That is a peppered moth. Which one has an advantage during the daytime if it's resting on a lichen when it comes to being spotted by a bird?
Peppered.
Yeah, the peppered form stands like is very hard to see. The dark one is more likely to get picked off. So let's take a look at British data. Why do we know this? Because British Isles are filled with butterfly and moth collectors, and there's a long history of data from all over on terms of how many they're finding. If you go back to earlier in the 1800s, when they were capturing these, what they would see typically is a very small number of dark moths and a very large proportion of peppered moths. But then that started to change. It changed, if you look at the figures in the lower right, the black represents the proportion of dark morphs. It changed most radically in England, particularly in southeast England and East England. Didn't change much in Ireland, hardly at all in Scotland during this time frame, and not much in Western Wales and some of those areas. So what was going on in the 1800s that changed this? It's called the Industrial Revolution, and the Industrial Revolution was built on burning coal. Now, coal had been around for a while, but this is when you really start to get factories and massive use of coal. I don't know how many of you are familiar with coal burning. I know I'm supposed to say, according to our government, now it's beautiful, clean coal. But anyway, I've actually seen coal. When I would go to visit my grandfather, we'd drive past the Ford Motor Rouge plant, and there are these big mountains of coal, and if it was wintertime, you would actually see black dust on the snow. We also had snow, and black grime everywhere. This is what coal does. It's beautiful, clean coal, and it leaves soot everywhere, which means that trees get covered with soot in areas where there's a lot of coal burning. Not only do they get covered with soot and get blackened, because it changes the acidity and kills lichens. So what you have in these areas as the Industrial Revolution develops is you start to see trees that look more like that. And who's going to get picked off by birds? Peppered form. So in areas which have lots of coal burning, we see a dramatic directional selection where now dark moths are being favored. So why don't we see that up here in some of these other areas? Although there are people there, and yeah, they had coal furnaces, you don't have the industrialization, the big factories and all that sort of thing pumping out the coal dust. So there's not nearly as much coal, and so in those areas, the change didn't occur. Later, in the 20th century, although coal is still an important fuel, there's a lot shift towards diesel and other types of power, and coal is less used, which means that less coal soot out there, lichens start to come back. In some of these areas, they're starting to see a shift back to the peppered form. This is, in fact, natural selection. It's not a speciation. This is all the same species, but it is a directional selection on a heritable trait occurring within the species as a result of environmental change, an environmental change caused by people. Here's another example. And the reason I like this is I can use it for all three selection types, although I think the last one's a bit made up. This is a peccary. And the peccary here is the selective agent. It's the selection pressure, because what we're actually considering is selection on the cactus. Peccaries like to eat the flowers of the cactus. Cactus defends itself against predators by using what? Yeah, spines, thorns, the prickly cactus. And for investing in spines is that costs. It's an investment to make the defense. If the defense isn't necessary, it won't be favored. the more serious the predation, the more important it is to make spines. If you're not having heavy predation, you're better off making more flowers, because flowers is how they reproduce. It's a trade-off. Before peccaries were found in an area, they tended to have fewer spines. There were still spines, there was always predators, but not as many. When peccaries entered the area, over time, over generations, you started to see a much higher percentage of thorns, I say spines, I should have said thorns, thorns on the cactus. Because their defense is becoming more and more important, because you have to survive in order to reproduce. So the selection pressure exerted by peccary predation on the flowers is pushing it towards a higher investment in defense. It's also a non-scientific name, peccary tajaku. Insular dwarfism is a directional selection. This is the evolution of smaller size in some islands. By the way, if you happen to be one of those people following it on the PowerPoints I changed today, because they've changed the subspecies of the Bali tiger last December. But at any rate, this is the Bali tiger population, the smallest tigers known. Also extinct since the 1950s. They were found on the Indonesian island of Bali, which is this island here. And they were the smallest tigers. For large animals that end up on islands, there's a strong tendency for them to evolve smaller size. We saw that earlier. What's the major reason for that? What's the selection pressure to be smaller?
It's not as much.
Yeah, lower resources. And so smaller gives an advantage in survival. This is the Cozumel raccoon, a critically endangered species of raccoon. It's 18% shorter and 45% less heavy than our common raccoons, including those that are nearby in mainland Mexico. It simply evolved to be a smaller raccoon. It's considered a separate species, although closely related, and is on the edge of extinction. Insular dwarfism can occur in other species. This is from chameleons on Madagascar. If one the mainland chameleons are larger in size. When you get out to some of the island types, they tend to get smaller. And then this little island, which is called Nosy Hera, I don't think this has anything to do with noses, it's probably something in the native language there, which is a small island. That's a fully adult gecko on that island, because the entire species is found on that island. The smaller the island, tend to have smaller evolution of smaller geckos. So insular dwarfism is a common trend found in many examples. Even on large islands like Borneo, which is a very large island, nevertheless the elephants on Borneo are actually smaller than Asiatic elephants anywhere else. So it can even work on larger islands, but of course it's more dramatic in smaller islands. That's where we get the elephants that are now extinct, but on those little islands I said that were like, waist high to a human, or even smaller. Oddly enough, we also have a phenomenon called insular gigantism, where organisms evolve to be larger on islands, but it's not King Kong. These are cases where you have an organism that starts out very small, like an ancestor of this. Weedas are not quite crickets, but they're cricket-like things found in New Zealand. On some of the islands near New Zealand, they've evolved to being fairly large. What is happening here is, first of all, they're not really, because they're small animals to begin with, the resource issue is not as important for them. When they get to the island, there's no predators. One of the reasons that it's not always good to become a larger insect is you just make a nicer target for the bird that wants to eat you. So there are various reasons why they wouldn't be evolved to these larger sizes, because they can't escape as well and so forth. But if there's no predators, that's not an issue. So that means why it's not bad to be larger. It doesn't tell you why it's good to be larger. Well, larger organisms can compete with each other better. Also, in animals like this, as we see this with elephants and a lot of things, based on what they eat, bigger stomachs and digestive tracts allow them to process food better because they're eating vegetable material. So if you remove the predation that says you gotta be small, then on an island where there's no predators, they may be evolved to be larger. They don't evolve to be the size of elephants for a lot of reasons, but they do evolve to be larger. That's probably as large as they could get and still function. Any questions about this, what the stabilizing idea, the directional ideas? That was the type of selection that we dealt with before. That's what you usually think of. If you set with modification, you tend to think of the modification means it's changing in some directional sense. It doesn't always work that way. Because environments can be relatively stable. If something is already well adapted, then it wouldn't need to change. Or you might have different selections operating on different ends of a range. So we'll look at examples of what we call stabilizing selection. In stabilizing selection, the mean doesn't change. The mean isn't changing because you have selection at either end. Either extreme is selected against, and the best thing to be is in the middle. Stabilizing selection actually tends to maintain genetic diversity. Remember how with the drunken fruit flies, how it increased, and then in the simulation you could end up with fixation? If an allele becomes fixed, that means all the other alleles are gone. So selection over a long term could actually reduce genetic diversity because only the favored alleles are being maintained. Stabilizing selection can maintain more than one allele because it might represent a compromise. In this case, here we have our peccaries, and we've seen how the peccaries were pushing it towards more spines. But we also have a different type of problem for the animals comes in. This is an insect that's a parasitic insect. And what it's doing is it's laying its eggs in the spines. And it's a parasitic insect that's bad for the cactus, which means the more spines it has, the more infected it is by the parasite. But on the other hand, if it doesn't have a lot of spines, it's being attacked by the peccary. So what turns out to be is some value in the middle is the ideal one. It can't eliminate the parasites, and it can't eliminate the peccaries because they're operating from opposite ends of how many spines you should have. So some compromised value will be what is favored. Stabilizing selection doesn't change the mean. Sometimes what it does is actually makes the curve more narrow over time. But it definitely is not going to change the mean. Now for a real, I'm not sure if this is I'm never quite sure from where I looked this up whether this is real or made up example. So this is what it is in a theory, selection against both means, extremes and the mean being maintained. So we can look at Norwegians. Nothing particular about Norwegians, this simply happened to be the data I found. This is birth weight, the weight of Norwegians when they're born, which is not that different from anywhere else in the world. You all have a pretty clear idea in your head, you probably do it in terms of pounds, of what the average size of a human baby would be. What's the number we usually say?
7.
Yeah, something in that range. We know, of course, that some babies are larger, some babies are smaller, but there is an average size. And it seems to be very stable, this distribution, over many generations. So let's think of the selective pressures. First of all, why not be bigger? Bigger babies could have various advantages. What is the problem about being there might be more than one, but what's an issue about babies that get too big?
Then end of them all during delivery and they take up too much resources.
Well, they certainly take up too much, they might take up too much resources from the mother. That could be an issue, although my aunt had carried identical twins, both of whom were 9 pounds, so that was pretty impressive. That was the last children she had. But at any rate, obviously there is that, and there's also, of course, what's the largest part of the baby? Its head. And what does it have to pass through? The birth canal. And prior to medical techniques like cesarean section, which haven't been around for hundreds of thousands of years, if the baby's head was too large, then what's going to happen? It's not going to be born, and the mother will die, and that tendency to have the bigger head is not selected for. Now, of course, we relax that a little bit, but it's still largely true. So that tells you why it can't be too big, but really tiny babies can pass through the birth canal quite easily. And extremely tiny babies don't take up much resources. So what's the selection against being really, really tiny? Especially in an era before intensive, care of.
It's not fully developed.
Yeah, it's not viable. There's a minimum size for viability. The minimum size for viability in intensive care maternity wards is different than it has been, say, 20,000 years ago. And most human evolution hasn't had intensive care maternity wards. So it's a fairly stable selection. This is also a stabilizing selection. This is the sociable weaver, whose scientific name means likes its neighbor and is very sociable. Sociable weavers live in what we call communal nests. This nest has many, many adults in it, so they live together. And their size is very stable, but it has 2 different selection pressures. Within the nest, being bigger is good, because then you can be the bully towards the others, you get better positions, more likely to mate. Being the bigger bird is good. But then they leave the nest and they're out hunting for food, and there are hawks and things looking for them. Which bird does the hawk want to go after? The bigger sociable weaver, and they don't have that much defense. So if you're too big, you probably won't be able to take advantage for very long of your ability to bully everybody else. If you're too small, the hawks don't get after you, but you're really living a miserable life and probably don't get much sex or anything. So they tend to have a very stable size range. I think since we're reached the end there, given where I am in the lecture, I'm pretty certain now that the test is going to be delayed from 1 day beyond. That may change some quiz dates. I'll have to look at that. I haven't really thought about that yet, but expect the test to be 1 day later than currently in the syllabus.